Okay, so let's look at the CPU time. CPU time is how much do we need to process a given job, okay, on the CPU. So we are not including about the I/O time, like receiving the data from the keyboard and then printing out to the screen. So we are not looking at, we are not considering. The CPU time is including two parts. It is including user time, user CPU time, which is normal program time, and system CPU time. So for instance, in your program, you are calling like a printf. Okay, so inside the printf, it is calling some system software. So we are excluding this part, then it's called user CPU time. Okay. So in general, the each program is affected by CPU and also system, like I/O system or memory or others. Okay, so first, in order to understand about the CPU time, we have to know about the clock mechanism. Okay, so clock is when you are buying the processor, or if you are opening your laptop, then it is saying that your CPU is like a i7, and the clock speed is 3.2 gigahertz, right? So this is clock frequency. So the CPU is operate based on this clock frequency. Okay, so this clock is constant rate clock. So for instance, it is 1 gigahertz. That means, let's say this is one cycle, and this is one cycle, and this is repeating. Okay, so this is one cycle, single cycle. This cycle is happening 1 gigatimes per second. Then we are saying that this is 1 gigahertz machine. Okay, so from the starting to the end, so it's periodically repeating, that is called clock period. One clock period. Okay, so 1 gigahertz case, there are 1 giga clocks per second. And so clock period is time for single clock. So for instance, 1 gigahertz machine. What's the clock period? So 1 gigahertz machine means per second there are 1 gigatimes clocks, right? So then per cycle, per clock, how much time do we need? We need 1/1 giga, right? Second. So each cycle, each clock cycle, each clock has 1/1 giga clock period. So 1 giga is 10 to the, how much is it? So you know that kilo, mega, giga, and tera, right? So 1 kilo is 1,000, 1 mega is 10 to the 6, 1 giga is 10 to the 9, right? 1 tera is 10 to the 12. That's the size. And second case, 1 second. And what is one over 1,000 second? That is called, what is called? That is called 1 millisecond, right? That's 1 millisecond. What is 10 to the 1 over 10 to the 6 second? It is called 1 microsecond. Right? 1 over 10 to the 9 second is called 1 nanosecond. Okay. 10 to the 1 over 10 to the 12, 1 picosecond. Okay. Okay, so at least you have to remember this merge, right? So 1 gigahertz, 1 gigahertz means each, so this is clock frequency. That means clock period wise is 1 nanosecond. Okay. So 1 gigahertz machine case, 1 clock period is just 1 nanosecond time. Okay. So here is saying that, so you let know that 250 picosecond means it's 0.25 nanosecond, right? So picosecond is 10 to the minus 12. And 4 gigahertz machine means this 4 times 10 to the 9 hertz. That's the 4 hertz. Okay, so what about there is a 2 gigahertz machine? Then what's the clock hertz, clock period? Can you type in the chat window? Yeah. 0.5 nanosecond. What about the 100 megahertz? Then clock period wise? Yeah, type in the chat window, please. Under megahertz, in the case, what's the clock period? Can you type in the chat window, please? Yeah, 10 nanosecond, right? Because this is equal to the 0.1 gigahertz. Okay. Okay, so that's the clock hertz. So clock is kind of heartbeat. So the processor is working based on this clock. If the clock frequency is high, then it can do more work per second. Okay. So CPU time is totally based on these clock cycles. Okay, and also how many cycles do we need? So for instance, if we have a program A, so to complete this program A, let's say we need 2 gigacycles. Okay, so we need 2 giga clock cycles to complete this program A. And clock period is 1 nanosecond. So per cycle, we need 1 nanosecond. Then what's the CPU time? So program A, we need 2 gigacycles, and single clock period is 1 nanoseconds. Then what's the total execute time? What's the CPU time? Yeah, that's the 2 seconds. Okay. So similarly, we have a program B, which is this one is required 1.5 gigacycles, and clock period is 2 nanoseconds. Then what's the CPU time? What is it? Yeah, please. Yeah, 3 seconds. Okay. So that's the CPU time. So if you know the number of clock cycles and also clock period, then you can compute the CPU time. Okay. So you have to know that CPU time is multiplication of clock cycles by clock period. Right? So this clock period is normally given. So for instance, if you are using the 2 gigahertz machine, in that case, the clock cycle is 0.5 nanosecond, right? So it's fixed. So if the process is given, then clock period is generally given. The only thing we have to do is we have to compute these clock cycles. So if we can reduce the number of clock cycles per program, then we can improve the CPU time, CPU performance. Okay. So here, this is example. So we have a computer A, which one is 2 gigahertz clock. And to complete this program A, we need 10 seconds CPU time. Okay. So the clock frequency is 2 gigahertz and CPU time is 10 seconds. Then here, what's the clock period on this machine? Hmm. 0.5 nanosecond. Okay, so this is clock period. Then to complete this program on computer A, how many cycles do we need? What's the clock cycles? How many cycles do we need? So simply, we are multiplying these two terms, then the result is to be 10 seconds, right? CPU time is, we already know the CPU time is clock period and cycles, right? This is 10, and period is 0.5 nanosecond. Then what's the cycle? It is 20 gigacycles. Okay. So to complete some program on computer A, we need 20 clock cycles. Okay. So we have this setting. Then what we are trying to do is we are designing a program, computer B. Okay. So here, what we want to do is we want to improve the performance. So our goal is we want to complete the program in 6 seconds. Okay, 6 seconds. So definitely we are increasing the clock frequency. Then we can reduce the CPU time, right? That's simple. But the problem is that because of this computer B is a new computer system, so clock cycles are increased by 1.2. Okay, so let's assume that clock cycle is increased by clock cycles increase to 1 point times. Okay, so initially it was 20 gigacycles, right? Now what is it? On computer B case, how many clock cycles do we need? 1.2 times more, so that 24 gigacycles. Okay, so this is given. So on computer B, we need 24 gigacycles. Okay, and where our aim is CPU time should be 6 seconds. Then what is clock frequency? What's the clock frequency? So we already know that CPU time is what? Clock period and clock cycles. And CPU time should be 6 seconds. Clock period, we don't know that. Cycles 24 gigahertz. Then what's the X? Hmm. 0.25 nanosecond. So clock frequency is 1 over X, which is 4 gigahertz. Okay. So if the clock frequency is given and clock cycles are given, or CPU time is given, so using these parameters, we can compute one of the parameter. Okay. Okay. So in general, clock period is fixed, right? This is fixed value. So if we can compute these cycles, then we can measure the CPU time, right? So the only thing we have to do is we have to compute clock cycles. It's totally depending on the program, right? Program. So if we are learning complicated program, then it requires more clock cycles. And also it is also depending on the computer system. Okay. So for each program, for each computer systems, the number of clocks are changing. Okay. So then let's make some equation for these clock cycles. So clock cycle is so if we have a program, so let's think about some C code, then there is some instructions, right? A equal B plus C, and D is B multiplication A, right? So there is some instructions. So we'll say this, each one is instruction. So definitely there are more instructions, then it takes more cycles. So clock cycles can be proportional to the number of instructions, right? So number of instructions are increasing, then in general, the number of cycles are increasing. And for each instruction, we have to pay some clock cycles. So for instance, each instruction, maybe it takes only 1 cycles, or some instruction case, it takes like 3 cycles, right? So per each instructions, maybe a different number of cycles are required. So we need cycles per instruction. Okay, so on average, per instruction, how many cycles are required? We have to know that. So this part is actually called cycles per instruction, which is simply CPI. Okay, cycles per instruction. So clock cycle is just number of instruction and CPI. So that's the clock cycles. Okay, so let's look at some example. Program A, there is program A. Okay. It has 1,000 instructions. So we have to execute 1,000 instructions to finish this program A, and CPI is 2. Then what's the clock cycles? So what is it? CPI is 2, and number of instructions is 1,000. Okay, then what is the clock cycles? Yeah, it's just simply 2,000. Okay, so let's look at another program. Example, program B. To complete this application, we need 1 giga instructions, and CPI is 1.5. Then what's the clock cycles? Can you type? 1.5 gigacycles. Okay. So then, let's summarize. CPU time is clock cycles and clock period, right? And clock cycle is number of instruction and CPI, right? So clock cycle is number of instruction multiplied by CPI and clock period. Okay, so the CPU time is proportional to the number of instructions to be executed, and also CPI, cycle per instruction, and then clock period. So per cycle, it takes more time, then definitely it takes more CPU time. Okay? So you have to remember the last one. So then let's look at some example. So this contents is appearing here. Okay, so I said CPU time is proportion number of instructions or instruction count, CPI, and clock cycle. Clock period actually. So we are saying that this is clock period. Okay, so here there is an example. Clock period. Let's look at there is a program A. And the number of instruction to complete is 1 giga instructions. And CPI is 2. And clock period is 1 nanoseconds. Then what's the CPU time? Very simple, right? 2 times 1 giga times 1 nanosecond, which is 2 seconds. Let's look at another one. Where B, number of instruction or instruction count is the same wording. Count is 2 giga instruction. CPI is 1.5. Clock frequency 3 gigahertz. Then what's the CPU time? It's very simple, right? So instruction is 2 giga and CPI is 1.5 and clock period is 1/3, which is 1. Right? So that's all. The CPU time case, we have to just measuring the how many instructions are executed and per instructions, how many cycles do we need? And then if we know the clock frequency, then we can measure the CPU time. Okay. Let's look at this example. So there are two computers, computer A and B. And each one has different clock cycle, clock period. The first one is clock period is 250 picosecond. And second one is clock period is 500 picosecond. And CPI is, the first one is 2.0 and second one is 1.2. And same instruction set architecture, which means that for the given application, number of instructions are equal, okay? So what this meaning is the instruction counters are equivalent. So then which is faster between computer A and B and how much fast? Okay, so that's our goal. So let me summarize. There are two computers, A and B. A case, clock period is, how much is it? 250 picosecond. CPI is 2. B case, clock period is longer, but CPI is smaller. 1.2. So in this case, which one is fast? So how much fast? So do you think which is fast between A and B? A. Do you think how much is fast? So A will be faster than how much A is fast? 1.2 times. So let's compute it. So there is some program, right? Program something from X. Let us assume that it takes X instructions to complete this program. Then what's the CPU time of A? It takes X number of instructions and CPI is 2 and clock period is 250 picosecond, right? That's the CPU time on A. CPU time on B is X and PI is 1.2 and 500 picosecond. So this is 500x and this is 600x. So means it's 1.2. So A is faster than by 1.2 times. Okay. So if we know the clock period and CPI, then we can compare the performance. Okay. If we don't number of instruction, the instruction count are equivalent. In that case, we can easily compare the performance of the computer systems. So here in this case, to improve the performance, what do we have to do? We have to reduce the clock period, right? So clock period getting shorter and shorter, then the performance is improved. And also CPI is reduced, then we can improve the CPU time, right? And also number of instructions to complete one program should be optimized. Okay, so then here, the most difficult part is, so here in this case, clock period that is fixed, right? Number of instructions, after we are compiling the program, then it's not hard to obtain how many instructions are actually executed. The most difficult part is actually measuring the CPI. So per instructions, how many cycles are required. So that is not easy part actually. So normally how they are doing is, simply they are actually measuring. So CPI, computing CPI is not easy. CPI is not easy. So what they are doing is, we always know that CPI times clock period and number of instruction, then it is CPU time, right? So we can measure the CPU time, and we know that how many instructions are executed, and we know the clock period, then CPI can be computed. So in general, we don't know the CPI value. So instead of that, we are measuring the other part, then we are computing the CPI in general. Let's look at some example. So there are 3 instruction class, okay? So this is A and B and C. So A, B, C are different instructions. So for instance, A is like add instruction, and B is like a multiplication, and C is like a division. Okay? So when you are doing the multiplication is more difficult than the addition, right? And division is most difficult, right? So division generally takes more cycles, more per instruction. So For this A type CPI, we know that CPI is just 1. Okay, so to execute addition instruction, we just need 1 cycle. For the multiplication, we know that it takes 2 cycles. Division case, we know that this takes 3 cycles. Okay, so we already know that. So this is given. This is given. Okay, so these are given. So that is fixed. Then we are executing 2 programs. So program 1. Program 1 case, there are 2 add and 1 multiplication and 2 division. So when we are looking at the program 1, it has 2 add and 1 multiplication and 2 division. So for this program 1, what is average CPI? What's the CPI value? So how many cycles do we need to execute this program 1? How many cycles do we need? So to execute this program, yep, it takes 9 cycles, right? Because this is single, double, triple. So we are adding all the cycles, then it is, how much is it? 10. It's not 9, it's 10, right? So for the program 1, we need 10 cycles. How many instructions for the first program? How many instructions? 1, 2, 3, 4, 5. Yeah, that's 5 instructions. Then what's the CPI value? Okay. So let's look at the second case. So this sequence. In this sequence, there are 4 add and single multiplication and single division. Okay, so we are looking at the second program. Like add, multiplication, division. So then what's the cycles, total cycles? How many cycles do we need to complete this program B, second program? So it's a single, double, triple. So it is 9 cycles. How many instructions? 6 instructions. Then what's the CPI? 1.5. Okay. So even for the same computer systems, per each program, the CPI is changing. Okay. So some application case, CPI can be very small, but for some other application, the CPI will be large. So CPI is not the fixed value. Okay. So CPI is totally depending on the which application you are running. Okay. So CPI is not a fixed one. So then 1, 2, 3. Okay. Plus 1, 2, A, B, C cycles. 1, 2, 3. So let's look at some example. There is another program C. So here it has 3A, 2B, and single C. Then what is CPI for this program? So there are 3 A instruction, 2 B instruction, a single C instruction on program C. Then how many cycles do we need to complete this program? Hmm. 3 plus 10. How many cycles? How many instructions? 6. Then CPI is 5/3. Let's look at the program D. 10, 2, 2. Then what's the CPI? Cycles are 20. How many instructions? 14. So CPI is 10/7. Okay. So now you can compute the CPI value, right? Cycle per instruction. Okay. So that's basic knowledge to compute the performance. Okay. So you have to remember the CPU value, CPU time is proportional to the number of instructions. So per program, and CPI and clock period. Okay. So instruction count, CPI, and clock. Okay. So we have to reduce each value, then we can improve the performance. Okay. So from this class, we are trying to minimize the number of instruction count and CPI and also clock period. Okay. So which one is affecting each parameters? So for instance, algorithm. So depending on the algorithm, algorithm means it is generating the different instructions. So definitely it is affecting the number of instructions and also CPI. Language, from language is depending on the CPI and also number of instruction. And compiler, number of instruction and CPI. And instruction set architecture, that means we learn about that. So what kind of instructions are available? So depending on that, it is also affecting the instruction count, CPI, and also clock period. Also, it's the hardware. So clock period is generally depending on the hardware. And this part will be software part. Generally. So we learn about that. So actually, this clock period is not easy to reduce. Okay, it's hard to reduce. So then maybe you want to reduce the instruction count or CPI, right? So there are 2 approaches. One is decreasing the instruction count, and second one is CPI, decreasing the CPI value. So there are 2 approaches actually. Okay, so then actually the easiest way to improve the performance is just increase the clock frequency, which means that decreasing the clock period. Then we can easily improve the CPU performance, right? So instead of 1 gigahertz machine, maybe 2 gigahertz is double, right? The performance is double. 4 gigahertz is much better. So what about the 10 gigahertz or 100 gigahertz? Why not? Maybe you cannot find it anymore. the reason is, so let's look at why it's not going to be possible. So this is power trend. Power trend means that how much power, how much energy is consumed on the processor. So processor is consuming the power, right? Energy, electronic energy. So the first one, this is clock rate, clock frequency. So clock frequency was increasing. It was increasing, and this is 2 gigahertz and 3.6 gigahertz. Then what is happening after that? It was fixed, it's peak. After that, clock frequency is actually reduced. Can you see that? Yeah, clock frequency is reduced. It's not going to be increasing anymore. Why? Because of the power consumption, energy consumption. So clock frequencies are low. In that case, power, the consumed power is not high. But if the clock frequency is increased, then power is increased. So at that moment, 3.6 gigahertz, the power consumption is 100 watt. That's a lot, actually. Can you guess how much is it? 100 watt? Maybe you are using some laptop, right? You're using the laptop machine. Laptop. Then you have the adapter, right? You have adapter. Adapter has this kind of things, I think. It has like a output voltage. Output voltage is 5 volt, and ampere. Ampere is like 6 ampere. Can you see that? So if you are looking at the adapter, then you can see that there is a output voltage and also output ampere, right? So voltage and current is actually power, which is 5 voltage and 6 ampere means 30 watt. Okay, so laptop is just consuming the 30 watt. But here, the CPU itself, single CPU is consuming 100 watt. It's amazing, right? So much. I think you are using this bulb, right? Under your room. It is just consuming like a 25 watt. So single small CPU is consuming 4 bulbs. So power consumption is a big part. Actually, power consumption is proportional to the heat. So if you are running some heavy application on your laptop, then the fan is spinning a lot, right? It makes a lot of noise. And also the keyboard is very hot. So heat is actually the problem. So the energy consumption means it is generating more heat, which means that we cannot increase clock frequency anymore because of heat. Okay, so later, what is happening? Actually, the clock frequency is decreasing, and also they are trying to reduce the energy consumption. Okay, so these days, they are not increasing the clock frequency anymore because of this energy consumption and also heat temperature problem. Okay, so that's the reason why the clock frequency is saturated. So after 3.3 gigahertz, later than the clock frequency is not going to be increasing anymore. Okay. So here, let me just. Okay. You know the voltage, right? Voltage is 5 voltage, something like that. And also you know the current. Voltage, current, I. Ampere, 3 ampere. Resistance, like 100 ohm, right? So maybe you heard about this thing, right? What's the power? Power P is just proportional to the voltage times current. That's power, right? That's the power. What's the relation of voltage, current, and resistance? Voltage is, yeah, V is IR, right? V is IR. So generally, if we are looking at the processor, the R is constant. Okay, after we are making the chip, the resistance part is not changing. So here we are providing the voltage, right? We are providing the voltage. If we are changing the voltage, then power consumption will be different. Okay, so power is VI, and I is V over R. So power is V square over R, right? So that means power is proportional to the V square. So for instance, you have one voltage. At that moment, power was 1 watt. Then if you are increasing voltage like 2 volt, then power consumption will be 4. Okay. So if you are increasing the voltage, then power is a square. So the opposite is also possible. If you are reducing the power, then power consumption will be dramatically decreasing. Okay. And so we know that this part. What about the frequency, clock frequency? Clock frequency and voltage. Relation of clock frequency and voltage. Actually, the clock frequency is proportional to the voltage. Why? Simply, you can think of the clock frequency is like this. On the chip, so this is chip. This is chip. Processor. If we are providing the high voltage, then we can easily drain the current, or we can supply the current to the processor, right? So we are giving high voltage, then the response, the current number of the content of the current will be higher, linear proportion to the current. So that if voltage is increasing like from 1 voltage to the 2 voltage, then the clock period can be reduced to half. So frequency will be like 1 gigahertz processor can be 2 gigahertz. Okay, so if we are increasing the clock voltage, then we can increase the clock frequency also. Okay, so it's proportional. So opposite is possible also. If you are reducing the voltage to half, then you have to reduce the clock frequency. Okay, because voltage is lower, that means it takes more time to drain the current or supply the current to the chip. Okay, so frequency is proportional to the voltage. Then what is happening? Let's think about it. We have some machine. So there is a program A, processor A. And this one has voltage is 2 volt, okay? And then on this machine, we are running program B. So we are running the program B on the process A, and currently process A is receiving the 2 voltage, and power, let us assume the power is 10 watt. Okay, to complete the program B. Then also execution time, it was like a 10 second. Okay, let us assume that this is happening. Then what's the total energy consumption? So energy is just power times time, right? So energy consumption is just multiplication of power and time. So energy is 10 watt and 10 second. That's the energy consumption, okay? So now what we are doing is we are decreasing the voltage to the 1 volt. Okay, so we are reducing the voltage to half. So then let's think about it. What's the power consumption? So what's the relation between voltage and power? If we are reducing, yeah. So it is, voltage is half, then power will be right? It's because of scarcely reduced. So 2.5 watt. Then what's the execution time on process A of program B? So it takes 10 seconds, right? On voltage 2 volt. Now voltage is to the half. Then what will be the execution time? Yeah, it is increased by 2. So it will be 20 seconds. Okay, because of voltage, if we are reducing the voltage, then the clock period is increased, so that the CPU time is increased. Then what's the energy consumption? Energy consumption is 50. It was 100, right? It was 100. Now it is reduced to half. So to complete a single program, same program, to complete that program, we just need half energy. So if we are reducing the voltage, then we can save more power, more energy. Okay, so then what the process company want to do? So process company try to reduce the voltage. Okay, but if there are much program, so program load is high, then they are increasing the voltage. If there are a small number of application on the processor, then they are decreasing the voltage. So what they are doing is, so modern CPU case, the voltage is changing. Voltage is changing. So the CPU is looking at the CPU itself, and if there are many applications, so it's always running, like it's 100% program is working on the processor, then they are increasing the voltage. That means power is increasing, energy is increasing, and heat is increasing, so that the fan is working. Okay, so that's why if you are running many applications on your laptop, then the fan is spinning. But if there is a single application and it's just using the 10% of the CPU resource, then CPU doesn't need to increase the voltage, right? Even though it slow down the program A, still is working, so they are decreasing the voltage. Okay, so they are adapting. So this kind of approach is called dynamic, voltage, frequency, scale. So modern processors are supporting this kind of feature. So if there are many, the CPU utilization is going higher, then they are increasing the voltage and they are consuming more energy and power. If the CPU utilization is getting lower, then they are decreasing the voltage and also the power consumption is reduced, energy consumption is reduced, and temperatures are going down. So that is much better, right? So this kind of thing is already implemented in the modern processor. Okay, so that's all. So you have just remember that power is just proportional to the V square and frequency is proportional to the voltage. So just you remember that. Okay. And also in many cases, if you are running this application, like for instance, CPU, and it is using the 100% or 90%, then maybe many processors running, and that means it is increasing the voltage, and then the temperature is going up. Sometimes the temperature is more than 100 Celsius. So if temperature is so high, then the process is not working anymore because of the temperature limitation. In that case, what they are doing is, if temperature is going high, then they are just turn off some applications. So if temperature is so high, then they are just reducing the voltage. That means the program is slowing down. So maybe you are experiencing this kind of thing. If you are running your application and the fan is working so hardly, but sometimes the computer system is getting slower, right? It's getting slow and slow because of this temperature limitation. Okay. So what they are doing is, instead of using this frequency, is not going to be increased anymore. It's not going to be possible because they have to reduce the voltage. What they are doing is they are trying to embedding more processor within a chip. Okay, so here this is the performance of a uniprocessor, single processor. So it was increased. It is following the clock frequency. This is clock frequency actually. Clock frequency. Well, as you know that this is 3.5 gigahertz almost. After that, the clock frequency is actually going down. So single core performance is not going to be improved anymore. So what they are doing then, they are using multiprocessor. So instead of just making a single processor, they are making, within a single chip, they are adding more cores. So core means it is actually different processor. So core means each core is just independent processor. It is also processor. Everything is processor. Okay. So the benefit of this one is, if you have a single core, and you have to learn 4 programs A, B, C, D. So there are 4 programs, and you have to, each one takes 2 seconds, and total time is 8 seconds, right? 8 seconds. So in order to do that, one you have to do is that you have to use like a 2 voltage, okay? But if you have 4 cores, then what is happening? 4 cores. Then each core executing each program. And then each core just takes completing each program like a second. Right? It's okay because there are 4 cores and each core is executing different program. So that in this case, frequency can be reduced. So it can be increased. This is like a 1/4. That means you can reduce the voltage also. So voltage can be a quarter. Then power consumption will be is a proportional to V square, right? It is 1/16. But there are 4 cores, right? So previous one has a single core. It takes single power, then now it is 4 times. So energy consumption is this one. There are 4 cores. So because of 4 cores, we need 4 times. So the energy consumption or power consumption will be water. So if we are preparing the more processors, then we can reduce the more energy consumption, more power consumption. So that means if we have 2 cores, then we can save energy by half. Okay. So that's the asymptotical analysis. So anyway, if we are using the multiprocessor, the benefit of multiprocessor is not just performance, we can also save the energy consumption. And also we can control the temperature. So that's the main reason why the modern processor has the multi-core machines. Okay. But anyway, from this class, we are focusing on the single core machine. So anyway, you have to remember the relationship between power consumption and why multi-core is coming out. You have to remember that. Okay, so that's all. So we are skipping this part. So next time we are going to the chapter 2, which is instruction set architecture. Any question? No question? Okay, then see you next week. Bye.